Alright, time for another DraftScience video presentation. Anyway, so responding to yesterday's video, there was a comment, so I thought it's probably worth reading. Blah blah blah. I've been puzzled with the basic and fundamental experiment for months. Okay, so this is a double slit experiment and all the woo that goes with it. Unfortunately, depending on how you're introduced to it, it's supposed to be some sort of consciousness. You know, if we're looking at photons, we change what they do and all this other crap. That's just crap. So the more deep you get into it, the more you understand how all that's crap. That it's the fact is that this is just an argument between, are there real variables changing what happens to the photons, or are there magical, innate properties of photons that they can do this weird and wacky things. And frankly, obviously, I'm like Einstein going to defend they're real variables. They're called surfaces and they're kind of obvious. But anyway, YouTube recommended your video and the other one for me recently. So this is to a Huygens optics video where I played it, a couple of his videos. I did respond in comments. He doesn't respond, blah blah blah. So anyway, from 9 minutes 10 seconds on. So he's a guy who does a lot of microscope type experiments. So microscopic double slit type experiments, which in a sense are kind of dangerous, just because the argument could be made that photons are rather large. They're really not microscopic. I mean, if we actually could see them, you'd be able to see them with a microscope, because they're thousands of atoms in size, frankly. But the problem is you can't see them because they're like an atom. Their substance is much smaller than their actual size. The little bits inside are smaller, and you can't see the little bits. Anyway, have you seen that question? Yes, a single photon is some way deduced by statistics and math. Now, the whole problem with their statistics and math is that they don't give the photon any dimensions. So they don't give it any length. So they think of a photon, when they're doing their statistics, as a ball. And they give it this infinitesimally small size. So it passes any one location in, a trizillionth of a second or something. Photons to them are not events that require a bunch of waves to hit the shore. It's just one wave hits the shore, that's it, photon. When I think logically people can understand that, no, it's more likely that a photon is a sequence of events, and therefore its length would be fairly long, because like the wavelength, it's thousands of atoms worth of wavelength, and so it becomes a rather large thing in space if you give it real dimensions, and then your statistics change. So when you make it a million times smaller than it actually is, then statistically you could say there can't be two of them at the same time. But obviously, if you make them more realistic in terms of their size, then statistically you can figure out that, oh, maybe they could be both. There could be two in the experiment at the same time. Let's see, I wonder if anybody has really made a single photon or electron source that would send one particle in a second. So again, there's no particle. There's no photon particle. Just like there's no atom particle. So I'm going to read some Feynman stuff after this comment. And, and he's calling atoms particles, and he knows they're not particles. They're composite objects. So why are we calling them particles when we know they're not particles? And we could follow the dual slit interference pattern after running the experiment in a dark room for a full day or something like that. Yes, so they did it in, the experiment in whatever, 18 something or other, 17 something or other, with a gas light, where they actually did do that. They took a whole day. But the idea of still using a single photon is kind of nonsensical, because technically, even if you're taking a whole day with a dim light, how you're stopping the photon is by putting an opaque barrier in its way. And the opaque barrier, okay, is essentially a bunch of slit experiments. If I make an opaque barrier, what I'm doing is I'm making a bunch of little openings that pieces of a photon can get through. So in a sense, I'm just saying, okay, here, I create an opaque barrier, I'm creating a bunch of diffracted light, and so I'm doing exactly by by what I would state is the reasonable theory of a photon. You're making elements of a photon all the time. There's little pieces of photon flying around all the time in the area, and what you're really doing is just saying, where did I duplicate the pattern? Because the photon is just the pattern. So where did I recreate the pattern out of the pieces? And so when you have a very few pieces, you'll have very little photons created. You have more pieces, you'll have more photons created. And it's just that simple, really. Alright, very good thinking behind the fact that there are 6 surfaces in the dual slit experiment. Well, you meant 8, I imagine. But you don't need to bother. See, the whole point of making slits is to point out that the diffraction is towards the matter. The slit is basically saying, I'm the surface. The electron is going out and it's going in. I can hit the electron when it's going out, or I can hit the electron when it's going back in. And when I hit it when it's going in, then I bend the light that way. I hit the electron when it's going out, I bend the light that way. So we understand why the surface is creating bent light in both directions. It can be in any one of those directions, just happens to be what electron it hit last was moving in what direction. And obviously how fast it's moving. The faster it's moving, the more you're going to get, the end result will be a more bent path for the photon, the energy of the photon, the reflection of the photon. I mean, what's really happening is, look, the little bit is hitting the electron moves, okay, adds this velocity to its already existing velocity, and the composite velocity, if it's going this way, will be something like this angle, or whatever angle it would be. And it depends on what the previous momentum of the electron was. So when it's really close to the surface, it might be moving faster than when it's further away from the surface. When it's moving, it's probably changing its speed as it moves out and in. Obviously, as it goes out, it slows down and stops, and then moves back in again, just like gravity. Anyway, not just 2D surfaces, which may cause classical diffraction. So 2D and 3D is sort of made moot, I think, by slits. Now, when you use a round aperture, then you're getting more into how you could be changing angles in both directions. So what do you think about quanta and entanglement ideas we have rooted deeply in society and technology today? Obviously, I have contempt for those ideas. If you watch some of my videos, you'll see that contempt is rather strong, that this is all just religion, this isn't science. They have so little evidence to speculate and to jump to these conclusions. They don't have anything near beyond reasonable doubt evidence, and yet they talk as if it's beyond reasonable doubt, that no reasonable person could deny their beautiful theory is beautiful, blah 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 blah. And I say, no, it's all unevidenced religion. It's just crap, most of it. Gigantic percentage. So I linked them to the video I did in response to the Huygens optics video. Alright, so off to the Feynman thing. Should be here, I think. Yeah, there it is. Alright, so this is one of the Feynman lectures, the second one. And I might as well read it rather than play it, just because it probably will go faster, I don't know. But anyway. Alright, so he did this is like just a preliminary thing where he hasn't gotten technical yet. He's just giving analogs for how to do physics and how to understand it. It's really, we're just following the bouncing ball kind of analogy. We're taking energy in the universe and following it through its different manifestations, kind of a story like that. So he says it's a little difficult to begin at once with the present view. So he's saying the present view of quantum mechanics is this wacky nonsense, so let's forget about that because it's going to hurt your brain if we just say this is the rule. First we'll explain how we got to that point, or where we were before we jumped into the silly sand. So we shall first see how things looked in about 1920. So this really isn't how things looked in 1920, because 1920 was already dominated by wave theories. Okay, 1801 is the Young experiment, and then you have the whole crap by the mathematician guy. These names. Anyway, the whole electromagnetic theory created by what's-his-face. Anyway, and then take a few things out of that picture. So the idea is this is what they thought, and we fixed it with crazy glue. And it really is just crazy, and it isn't very gluey. Before 1920, the world picture was something like this. The stage on which the universe goes is the three-dimensional space of geometry. So this is as described by Euclid. So, they're going back to the first guy who talked about it, but maybe, this is like a flat earth, round earth kind of thing. This is the kind of thing that a lot of people probably observe, that the reality seems to have these three dimensions in it. I can go forward and back, I can go left and right, and I can go up and down, 3 dimensions. 6 subdimensions. I'm sure it occurred to an awful lot of people. And yes, I would argue that is the reality. The real universe does have 3 dimensions. Everything happens in that absolute space. There is no whatever bent space-timey bullshit. Okay, and things change in a medium called time. So there's no medium called time, there's just a function called time. So time just means that things move from point A to point B, and they move slower than instantaneously, and therefore there's such a thing as time. Time is a consequence, it is a byproduct, and it isn't really a thing. Okay, it's just a byproduct of the fact that the universe doesn't happen instantaneously. Things move slower than instantaneous, and therefore there's a universe. The elements on the stage are particles. They don't believe particles, okay? So they say the word particle, but they have, it doesn't mean anything to them. It has no structure, because they'll sit there and say an atom's a particle, when we already know an atom's not a particle. It's a bunch of empty space with a couple of little elements in it. Little tiny, tiny elements of momentum. For example, in atoms. So see, what a terrible example, right? We know the atom is made out of particles, but the atom itself isn't a particle, which have some properties. Okay, so he's calling an atom a particle, and then he's talking about its properties as a particle. Well, it doesn't have properties as a particle. It has properties based on the fact that it's made out of 2 different charges, electrons and protons, the 2 different kinds of matter. First, the property of inertia. So there is no property of inertia. Okay, there's just the fact that if you're going to give something momentum, the fact is it takes time to give it to it, and you can only give it what you got. It doesn't resist being moved, it just waits until you move it. You have to give it water before it has water in its glass. Glasses aren't saying, I'm opposing the water. It's not opposing anything. Okay, you have to pour the water in. Fact. So there's no inertia. Okay, it's just a kind of another one of these concepts that is, in my opinion, just a wrong concept, a wrong way of thinking about it. Just like thinking about momentum as being something other than money. You could argue that your motion is a kind of money, and all you're doing is exchanging your currency. And there's just a difference between 2 things. When they're in opposition, one has anti-money and one has money. So, but the relative differences don't matter. You don't have to have actual velocity. It just means that in every interaction you're having, there's an actual difference between your velocity and its velocity, or you wouldn't be having an interaction. If a particle is moving, it keeps on going in the same direction unless forces act upon it. So this is, again, if a particle. So the statement would be, no, but we know that the atom isn't a particle. We know it's made up of particles. We know the particles inside of the atom have to do the actual moving for the atom to move. So the electrons and protons are the things actually moving. They're the things with actual mass. They're the things with actual momentum. They're the things gravity is actually moving. Gravity doesn't move atoms, just like we aren't moved. We don't move. the atoms we're made of move. We don't do it. They do it. So it's a really, in my opinion, a horrible perversion, okay, of the proper way to understand the mechanism. And again, unless forces act upon it is true, but the understanding has to be is that the electrons and protons are always being acted on by forces. They're in a constant field of energy, a constant bombardment by the universe of photonic energy that makes photons. Little bits of momentum are hitting it constantly. It's never not in being acted on by a force. Its entire existence is dictated by it, and that means that when it does travel or gain some velocity, it can only maintain that velocity because of some other mechanism. Protons and electrons are dragged to a halt, so it doesn't have to be acted on by some direct force. Just moving into the energy will drag electrons and protons to a stop. They can't go forever. The second element then is, so just to make sure, so he's making a rule for particles. If a particle is moving, it keeps, no, it's not a particle. If an atom is moving, it keeps on moving, not a particle. And an atom has to, and the reason why the atom works is because the atom has the helium nucleus inside of it, and that's the thing that makes the difference. And the helium nucleus is essentially what you would, I mean, you go into neutrons, and then you can go into the fact that a neutron is really just a very tight hydrogen atom. The second element then is forces, which are then thought to be of two varieties. So now I would just re-describe this as we know there's two kinds of elemental matter, electrons and protons. See, he's doing it like he's pretending he's talking from 1920 perspective, but the 1920 perspective wasn't full of 17,000, muons, duons, gluons, squons, quarks, blorks, all this other, baby talk about all these magical particles. So before 1920, you just had electrons and protons to worry about. That was what matter was made out of. That was the thing that made atoms. Atoms weren't full of muons and taus and all this other crap. First, an enormously complicated, detailed kind of interaction force. So none of that's necessarily true. He thinks it's enormously complicated because he has a bad view of it. So it seems like very confusing how it behaves because he doesn't understand it elementally. Okay, detailed kind of interactive force which held the various atoms in different combinations in a complicated way. Now it's only complicated because there are plus and minus charges in the atom, and depending on how you're looking at the atom, you see either the plus or you see the minus. If the electrons are towards you, closer to you than the proton is, it's further away. If I'm changing where they block each other. So close up, I'm going to see the electron. Further away, the proton's bigger, the electron's going to get very smaller, and so it's only going to be a little dot in front of the big giant proton, so it's going to look very proton. It's going to look very positive from a distance, very negative up close. Just like the moon's around a planet. If I'm very close to the moon, the moon's here, the planet's here. If I'm very close to the moon, I can't see the planet. If I'm very far from the moon, I can't see the moon. And all I see is the planet. Alright. So it's not complicated, blah, blah, blah. Which determine whether salt would dissolve. First is enormous kind of interaction held in various atoms in different combinations in a complicated way. So the atoms connect to each other because first you have to understand how they're connected. They think the electron's swirling around and it's being held by a kind of gravity. I say complete nonsense, that it's all magnetic, and so all you really do is have them in locked positions magnetically. So there's 100 different kinds of ways you can arrange the geometry of electrons and protons and create a stable configuration where magnetically all the north and south sides are flipped just the right way, where the configuration just stays in place because the opposite charges repel and the like charges attract. And the fact is that the attracting charge can't get closer without getting closer to the repulsive charges of the other electrons, and therefore they're locked in position magnetically. Alright, which determine whether salt would dissolve faster or slower when we rise the temperature. The other forces, so that just has to do with how much energy. That has to do with, say, you're heading towards a planetary system and of moons, a planet with moons. And the idea is if you miss the moons, you can get to the planet really easy. But if you head in and you hit a moon, well, then the moon's going to repel you, and now you're not going to be able to get into the inner circle, of the planet. So depending on how you go in, how much energy you have, will decide. If you have enough energy, then you push the moon out of the way, and you can get into the atom, so to speak, into the inner part of the atom. The other forces that was known for was the long-range interaction, a smooth and quiet attraction, which varied inversely as the square of the distance, and was called gravitation. So we know gravity's a small effect on the subatomic level, that the electrons and protons are really interacting with each other based on their charge, and there really isn't any gravity, because charge becomes gravity when you have an object that has all the charges in mixed directions. So if I mix all the charges in mixed directions, I lost all of the identity of the charges and have neutralized them to compensating for each other, crossing each other out, so to speak. And it's only when I align all the atoms that I can reveal the magnetism that lies at the core. So the magnetic and electric ideas, the idea of charge and magnetism, are the rudimentary function. Charge is the rudimentary function. It becomes magnetism when you imbalance the charges. Then you have a magnet, you have a dipole. When you have more electrons on one side and less electrons on the other side, blah, 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 then you have a dipole. Once you create a dipole, you have magnetism. Alright, this law was known and was very simple. So it wasn't correct. It was already, and again, Maxwell, the guy's name I forgot earlier, had already, turned it into mush with a bunch of, not that the math is all that wrong, but the interpretation of why it happens is wrong. There aren't an electric field and a magnetic field, there's just the charge fields. Why things remain in motion when they are moving, or why things remain in motion when they are moving. So that's not a true statement. Electrons don't remain moving, and protons don't remain moving. You can't shoot them to the moon. They won't make it. Okay, or why there is a law of gravitation was, of course, not known. And again, it wasn't known to them. It wasn't known to certain physicists, but I'm sure somebody had speculated, as somebody did 350 years ago, that maybe gravity is just another form of the force. It's just particles, pieces of momentum, and it hits matter, and it hits the matter based on how much matter you have. And so if you're standing in the rain with a bucket, if you're heavy, you have a big bucket, you collect lots of rain. If you're small and light and have very few atoms, you have a very small bucket and you collect very little rain. And the rain is going to be your momentum. A description of nature is what we are concerned with here. Yes, we're looking for a correct model of the truth, a correct way, correct statements describing it. And you're already screwed up when you call something a particle that you know isn't a particle, like an atom. You know it's not a particle, so forget it. It's not a particle. A photon, I think, a logical person could know, it can't be called a particle because it has to be made out of waves, in the sense that it has to be made out of constituent parts. More than one thing has to happen for you to have a frequency and a period. You can't make a period out of one object. You have to have numerous objects land before you can say, there's a period between the events. A dot, just going dot, is not Morse code. I mean, to have Morse code, you have to have more than one dot. From this point of view, then, a gas, and indeed all matter, is a myriad of moving particles. Right, but let's understand the elements. That the whole point is to say the universe has elements in it. So I would argue there's two kinds of force, electron force and proton force, and two kinds of material bits, which are electrons and protons. And neutrons are just a composite of a proton and an electron very close together. And that's it. That's all there are. There's just electrons and protons. There's just positive charge and negative charge, and there's two forces that go with those two charges. And that's it. And the rest of it's just two interactions that can happen. You can push an electron, or you can have your force deflected. And that's it. Thus, many of the things we saw while standing at the seashore can immediately be connected. First, the pressure. It comes from the collisions of the atoms with the walls or whatever. Or whatever. I guess he's saying the seashore, the sand, the bottom of the ocean, and the atmosphere. The drift of the atoms as they are all moving in one direction on average is wind. The random internal motions are the heat. Everything's just momentum. And the momentum gets transferred from one object to another object. And that's all there is in the universe. It's that simple. There's little objects called force, bits, that have momentum. They give their momentum to bigger objects called electrons and protons. The bigger objects create the emergent velocity of the object that contains the matter bits that are moving. Okay, but it's all just transfers of momentum. There are waves of excess density where too many particles have collected, and so they rush off. They push up piles of particles further out, and so on. So I guess he's talking about like foam or something. Crashing waves. This wave of excess density is sound. Okay, so again, the sound isn't really excess density. It just has to do with the fact that the atmosphere is made of these atoms, and if you want the sound to be able, you want the momentum to stay durable, it has to be at a sufficient speed. If the movement isn't of the sufficient speed, then it's destroyed by scatter or kind of friction in the atmosphere. So the motion is less frictionful if the impacts between the atoms are quick enough. It's like if you roll a cue ball into another pool ball slowly, it doesn't do the Newton's cradle thing as well. So the faster it's moving, the more likely it is to make an effective transfer. And the less velocity it has, the less likely it is to be an effective transfer, and there's more frictional noise, and so more scatter. So energy that's not scattering is sound. Okay. It is a tremendous achievement to be able to understand so much, and so they don't understand. And then he's talking again about what they understood in 1920, and that's the physics they destroyed and stomped into the ground with their silly, wooey magic crap. Some of these things were described in the previous chapter, so yeah, he used other analogies to describe what we're trying to describe in terms of modeling how the physical universe functions. What kinds of particles are there? So we're again saying the word particle doesn't mean anything, but anyway, because they don't use it seriously. There were considered to be 92. So again, he's overtly calling atoms particles. And it's just, just messes up the meaning of the word. Okay, at the time, 92 different kinds of atoms were ultimately discovered. So we know it's 92 different arrangements of electrons and protons. Durable geometries for putting them, electrons and protons, in certain positions. And there's 92 ways to arrange them that are sustainable, that stay intact. Generally speaking, I mean, some of those 92 aren't very stable. Actually, frankly, their stability is they will combine with some other element. They will connect to it and stick to it and get immersed in it. But some of them have half-lives. I mean, they decay almost instantaneously. I mean, as soon as you make them, they decay really fast because they're not stable. They had different names associated with their chemical properties. The next part of the problem was, what are the short-range forces? So this wasn't a problem for anybody. This was just stuff they're going to make up, because they really did, this is inside the atoms. Why does the carbon attract one oxygen or perhaps two oxygens but not three oxygens? Obviously, it just has to do with how many magnets are in the way, what the shape of the magnetic field created by the atom is. What is the machinery of the interaction between atoms? So this is all stuff that they can't figure out because they don't have an elemental model that's reasonable or rational, and they didn't have one in 1920. Is it gravitation? The answer is no. Well, they figured that much out. Gravity is entirely too weak. So gravity is not weak. Gravity is magnetism and charge. It's just that it's not going to be able to manifest the strength of charge and magnetism because you're pointing the gun in every direction. You know what I mean? There's no, you've gotten rid of the biases that make the force, that give the force real power. All right, gravity is entirely too weak. Gravity is the consumption of some of the energy you're pulling out of charge. Okay, but imagine a force analogous to gravity, varying inversely with the square of the distance, but enormously more powerful, having more and having one difference. In gravity, anything attracts everything else, but imagine there are two kinds of things, and thus the new force, which is the electrical force, of course. There's no such thing as an electrical force because electricity is really a phenomenon of atoms transferring electrons. And so there's just charge. Has the property that it likes repel and unlikes attract. So the simple two interaction thing. The electron force pushes electrons. The electron force is deflected by a proton, and vice versa. And with that simple mechanism, you create attraction in the circumstance of unlike charges, and you create repulsion when they're like charges. Alright, the thing that carries this strong interaction is called charge. So again, charge is the byproduct of the fact that there are that protons react differently to the two different forces. Okay, then what do we have? Suppose we have two unlikes that attract each other, plus and minus, and they stick very close together. Suppose we have another charge some distance away. Would it feel any attraction? It would feel practically none, because if the first two are equal in size, the attraction of one and the repulsion of the other balance out. So that's sort of what I was describing before, position. So where you position yourself, where you're looking at an atom, decides whether the atom looks positive or whether the atom looks negative. If the electron's in front, it looks negative. If the electron's over here, it looks positive. So it looks different depending on your place you're looking at it from. Suppose you have another charge, practically because the first one are equal in size and attraction of one, repulsion of the other balance out. Therefore, there is very little force at any appreciable distance. So yes, the further away you go, the more the two charges are neutralized in terms of they become the same distance relative to your distance. The amount of difference between the electron's position and the proton's position becomes moot at a distance because it becomes a tiny percentage of the total distance, and therefore you can't tell the difference between the two lights. If you have two lighthouses and one of them's a mile from the other, when you're right next to one of them, the one that's a mile away is a lot dimmer. But if you go a mile away from both of them, then it's only 1 mile and 2 miles. And if you go 5 miles away, then it's only a tinier percentage. And then you go 10 miles away, the difference, that 1 mile, is now only 10% difference. So you keep lowering with the differences between the intensities of the two sources based on how close you are to one or the other of the sources. On the other hand, if we get very close with an extra charge, attraction arises because the repulsion of likes and attraction of unlikes will tend to bring unlikes closer together and push and push likes further apart, then the repulsion will be less than the attraction. Well, obviously, as you get close to an atom, with an atom, they're going to be naturally repulsive because our electrons are on the surface, and the electrons are likely to interact with each other and cause repulsion that's stronger than any of the attraction. And that's why, to combine things, you often need to force them to move very quickly so they push past the repulsiveness of the electrons and force the new electrons to get inside the old electrons. The electrons of one atom have to get pushed beyond the position of the electrons in the other atom for the two atoms to now create a new configuration. This is the reason why the atom, which are considered out of plus and minus electric charges, which are constituted, feel very little force when they are separated by appreciable distance, aside from gravity. So again, what they're feeling can only be charge because there is no gravity. Gravity is just charge neutralized because it's in all directions. When they come close together, they can see inside each other and rearrange their charges, right? So you're just going to rearrange the electrons and the protons and create a new configuration that'll be your new compound. With the result that they have a very strong interaction. The ultimate basis of the interaction between atoms is called electrical, but it's really magnetic. And Feynman will just say electrical and magnetic are the same thing anyway, so he could have said magnetic here instead of electrical, since this force is so enormous. So again, there's no electric force, there's just charge forces. The forces have charge because they are plus and minus, because they are electron and proton forces. All the pluses and all the minuses will normally come together as they intimate a combination as they can. Intimidate a combination as they can. Anyway, all things, even ourselves, are made of fine-grained, enormously strong, interacting plus and minus parts. And so, that's an okay statement. I mean, charge is everything. All neatly balanced out. And let's understand what charge is. Okay, charge is just like, say, if I have two ping pong paddles and I have a ball that never slows down. And all I have to do, so I have one ball bouncing between the two paddles and it never slows down. And every time it hits the paddle, it imposes momentum. It's a force. It pushes at the same amount. And so all I do is put the two paddles closer together, and I've doubled the number of interactions. I've doubled the number of momentum transfers. So you can sort of understand that's how charge works. When electrons get very, very close to each other, an awful lot of interactions between them, and all that insane number of interactions means there's an insane amount of energy trying to push them apart. Once in a while, by accident, we may rub off a few minuses or a few pluses. Usually it is easier to rub off minuses, and in these circumstances we find the force of electricity unbalanced. So you're just changing the balance of your charges. So evacuating electrons means that you're going to have less agitation between the atoms, and we can then see the effects of these electrical attractions. Alright, to give an idea of how much stronger electricity is than gravitation, consider 2 grains of sand a millimeter across, 30 meters apart. The forces between them were not balanced, and if everything attracted everything else instead of likes repelling, so there was no cancel. How much force would there be? There would be the force of 3 million tons between the two. So he's applying the strength of the maximum strength, you could argue, of the electron force in trying to make it into a larger object, and try to say that a grain of sand has 3 tons of force behind it or something. I think that's excessive, but whatever, it doesn't really matter. You see, there's very, very little excess or deficit of the number of negative and positive charges necessary to produce appreciable electrical effects. The point is that the more you can purify the force, the more you can understand that there's so much yin yang, and it's only a tiny percentage of the total amount of difference you could make. You have so much blue and so much red, and the fact is that you know, it's always purple, and we just make it a little bit bluer or a little redder. We can never really get pure red or pure blue. And if we did, it would be a million times more blue than, you know, the bluish purple we're looking at. Alright, anyway. Charged or uncharged things. So a few particles are involved and hardly make a difference in the weight or size of the object. So it just takes a tiny number of changes in the electrons, the total number of electrons on a surface, to instigate a substantial increase in the charge, or the how much it's going to be repelled or attracted. Alright, with this picture of the atoms, the atoms were easier to understand. They were thought to have a nucleus at the center, so why would you call them a particle then, right? So let's understand the nucleus isn't a particle, which is positively electrically charged and very massive, and the nucleus is surrounded by a certain number of electrons. So again, they're telling you what their mass is, and we understand that the only way we detect mass is to put something in gravity. We can't detect mass in some other way. We can only detect it by putting a certain amount of force against it and then saying how far or fast does it move. And it's hard to do that with electrons and protons. So measuring their actual mass versus measuring their charge is probably, in my opinion, not very practical, but whatever. Which are very light and negatively charged. You know, there's just no scale you can put an electron on where it isn't already repelled to the scale, you know, where it doesn't have a charge reaction. Now we can go a little ahead of our story and remark that in the nucleus itself there were found two kinds of particles, protons and neutrons. So we already knew neutrons decay into a proton and an electron, so why are we playing a game that a neutron is a particle? It's not a particle, it's a composite object. And it's just made out of the elemental ones, the electron and proton. And that's all there are. Muons, puons, duons, quarks, blorks, all this stuff has to be made out of the force or the matter. It can't exist as some other entity. There's just electrons and protons, then there's just electron force and proton force, and you can create configurations of it and give that a name, but there's no such particle. It has to be made out of these elemental bits, almost of the same weight and very heavy. The protons, it's very heavy because it's in a nucleus, you know, frankly. But the fact is the protons end up in the nucleus, and that indicates that they probably don't have as much momentum as the electrons. They're not easy to give them momentum, so that's why electrons end up on the outside of atoms and protons end up on the inside. They are different. Okay, the protons are electrically charged and the neutrons are neutral. So the neutron isn't neutral, depending on how you're looking at it also, because it's clearly just the fact that if it's spinning, that is, the whole atom is spinning, it has an electron and a proton, and it's spinning, over any given period of time, it's always going to look the same. As much red face is going to show as blue face, so it's always going to look purple. And it is surrounded by 6 electrons, negatively each ordinary joule matter of electrons, very light compared to, so this is just blah 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 blah. So this would be an atom with number 6 in the chemical table. It's called carbon. So he's just describing how you make the different elements out of different arrangements of electrons and protons and neutrons, but again, neutrons really should just be counted as electrons and protons. And in fact only upon how many electrons there are. So the chemical properties of a substance depend on the number of electrons. No, the chemical properties depend on the geometry, not the number. How they are shaped, and how they're shaped is dictated by the number. You can't make a square out of 3 points, right? You can make a triangle. So, you know, the geometry, the number dictates the possible geometry, and whether it's symmetrical or not symmetrical. The whole list of elements of the chemical reality could have been called 1, 2, 3, 4, 5, etc. Yes, so the elements are just a certain number of arrangements that work, and we could have just numbered them. But yes, he just says symbols and names are probably better than numbers. Okay, so it's not really important stuff. And maybe the rest of this isn't all that important because he does get kind of just rambly here. So maybe I'll come back to it. Because eventually he's just going to get into muons and gluons and puons and start throwing all this crap into what is this very simple. It could have been a very simple universe, and instead he turned it into he's turning into a mushy, complex one. So yeah, this is about just charge and a comb. I mean, this is all basic stuff. Here is an analogy. If we were in a pool of water and there was a floating cork very close, so this again is just the argument about how the force changes depending on how close you are to the electron or the proton. Which side of the atom you're viewing it from, you'll see a different thing. But they're not saying it that way. They're not understanding it that way. They're saying the difference is some kind of intrinsic thing. Some sort of, the atoms just like to have fun. Cyndi Lauper song, atoms just like to have fun. It's just, it's not just, it's happening, there's strict cause and effect. Strict cause and effect is lost in here. So Feynman doesn't do much cause and effect conversation. And so eventually it gets to quantum mechanics and really screws the whole thing up. So anyway, hit this part here on, alright, the electromagnetic field can carry waves. Some of these waves are light. So they're not waves, they're just a frequency in a composite substance, okay, that hits a surface. And by hitting at a continuous frequency, you can end up causing an electron to be transferred between atoms and to change its momentum, and if you get the electron moving fast enough, it will lead the atom. Alright, these oscillating waves can have various frequencies. The only thing that is really different from one wave to another is the frequency of the oscillation. So again, it's just the frequency between the bits of the event. Okay. If we shake a charge back and forth, so when he's saying shake a charge back and forth, move an electron from here to here, that's the same thing as me just moving my hand from here to here. My hand's moving away, I'm reflecting less. When my hand's moving towards, I'm reflecting more. And that's all that you need to know. That's the field. When the electron moves in space, it changes the field. It reflects more field when it's moving towards you, and it reflects less field when it's moving away from you. Fact. Less energy hits you when my hand moves away than when my hand moves towards. So all of this could be understood much better if they understood that simple fact. Electrons don't have some magical powers. They're just, the fact is they're opaque. And so when they move this way into the force, they reflect force. When they're moving this way, it means they're moving away from force going this way, and they'll not reflect it as much. And that's all it is. It's just about, the fact is that you're a reflecting thing in the universe, and every little bit in the universe, all the constituent little bits, are constantly, depending on their motion, going to reflect to the universe a different appearance depending on which way they're going and which way you're looking at them from. So if they had reduced all of this into that, it would have been so much better. So he's into wave-particle duality here, recognizing that all there is the frequency and blah, 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 but still talking like there's some sort of thing called a wave, and then he says there's X-rays, but the X-rays are more like particles, and less like waves. It's just kind of mush. So anyway, that's probably enough. And such, and so forth and whatnot. If somebody knows how to steal these audio files, I mean, I did a little looking. I mean, there's got to be the MP3s or somewhere, where you could actually load them. So it's Feynman Lectures at caltech.edu. Because it would be nice to be able to play them a little bit faster, and the player they provide doesn't do that, and so it's a little bit irritating. Anyway, blah 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 blah. So I think that's all we need to do here. Yeah, that's probably enough. Enough of a video. So, yeah, till the next time and such. So this has been a DraftScience video presentation. Yeah, that's all. For what purpose? Who's listening? Yeah. Who? Who's smart enough to get it? Yeah. That I got it. I got the right answers. I got a lot better answers. You ask a question, I have a better answer. It's just a fact.